Great. Well, welcome everybody to this talk track session. First up, we have James Lamb here, who's going to talk about how distributed LightGBM on Dask works. James is actually a colleague of mine at Saturn Cloud, so I know it's going to be a great talk. I've seen some of the content. So you can go ahead and take it away, James.
All right, thank you. And hey, you don't know how much of the content you've seen. Okay.
Love new stuff.
Fantastic. Yeah, so good morning to all of you. At least it's morning here in Chicago. I'm really happy to be here talking about LightGBM. So my name is James Lamb. I'm an engineer at Saturn Cloud and a maintainer on the LightGBM project. Today, we're going to talk about what LightGBM is. I think it's important to understand how it works before we can talk about how it works with Dask. And then in the sort of second half of the talk, we'll talk about how the Dask integration of LightGBM works specifically, and a little bit of like fun history there. So let's get right into it. And as a disclaimer, I'm an engineer at Saturn Cloud. We're a company that produces a managed data science platform, which includes a managed Dask offering. But we're not going to be talking about Saturn anymore today. All right, so first let's talk about what LightGBM is and how it works. LightGBM stands for Lightweight Gradient Boosting Machine. So LightGBM was introduced by Microsoft Research in 2016 in these two papers. And in these two papers, the original authors of LightGBM laid out an approach to solving supervised learning problems using gradient boosting, where each learner in the boosting step is a tree. Supervised learning problems, that refers to problems like classification, will this person default on a loan? Regression types of problems like what rate should we offer this person for their loan? Learning to rank types of problems like when someone types in this particular query, what results should we return? And multi-class classification types of problem. And that's like, okay, based on this customer's details, which of our like market segments do we think they fall into? Stuff like that. Let me explain a little bit about how gradient boosting with trees works in general, and then we'll talk about how LightGBM works specifically. And I think that this little graphic down here describes it fairly well. This is from a blog post called Gradient Boosting Explained. I recommend checking it out. It's really nice. And the way that this process works, we're building tree-based learners similar to what you might have experienced with, say, random forest. I think, most people who have experience with tree-based machine learning, random forest is like one of their first sort of introductions to that space. However, unlike the random forest, in a gradient boosting machine, you can't train all of the trees all at once. Instead, what happens is you train the trees one at a time, and this is where the boosting process comes in. And so what happens is when you start with a task, let's say it's a regression task, like predicting how much it's going to rain today or something like that. You start with some training data. Those are features, input data that maybe describes that outcome, and then an actual measurement of the outcome itself, sometimes called the label or the target or the response. The boosting process begins with an initial guess for what every record's value of that target will be. You can supply your own in a lot of boosting frameworks, or the framework will choose a sort of reasonable default based on the problem you're solving. So for a regression problem like that, we may just say, okay, our first guess is just like the rainfall today will just be the average rainfall that we've observed over the whole data set. No problem. Then what happens is that residuals are calculated between the actual values of the target and that first guess. A tree is trained on those residuals. And so the first tree, its job is to explain the mistakes made by that initial guess. And that tree-based training process works, sort of like other tree-based training processes. Each of these little circles in the tree represents what's called a split. A split is a rule that combines a feature and a threshold. So this might be like, if humidity less than 10, whatever the units for humidity are, 10 units, then that data goes to the left of the tree, and greater than 10 goes to the right of the tree, something like that. The process involves, adding more of these splits to get a better and better description of those residuals. And then once tree growth stops, LightGBM says, okay, do I need to add another tree? And that's based on a couple parameters we'll talk about in a minute. And if the answer is yes, then what happens is now the output of your model is that initial guess plus the outputs of this first tree. Then a second tree is trained on the residuals between that new guess and the actual values of the target. And this just continues and continues and continues. So this is where the boosting process comes in, where each tree is basically looking at what the model is getting wrong so far, to oversimplify. And so this raises some like interesting problems for thinking about parallelizing this, right? Thinking about doing this in a distributed way. We are at the Distributed Summit because there are some synchronizations that have to happen here, right? We'll get into that. Okay, so LightGBM, the project. LightGBM is implemented in C++. The core library is written in C++. All of the boosting out, like different types of boosting algorithms, et cetera, et cetera. And then there are a bunch of wrapper packages. There's actually a CLI. You can brew install LightGBM and just like use it from your terminal like you use Git. Kind of cool. There's a Python package, an R package, a Java interface. There are GPU accelerated versions of all of this and like tons and tons of other integrations. The one that I'd like to talk to you about today is the Dask integration, and that's part of the LightGBM Python package. But the first like important thing to take away from this talk is when you use LightGBM on Dask, all of the LightGBM algorithm has not been converted into sort of like Dask native operations, into delayed functions and like map blocks and map partitions and like all that fun stuff, right? What's going to happen, you'll see in a little bit, is that we're using Dask basically to move data around and to set up the LightGBM network, but then the actual like core logic of the training is happening in LightGBM C++ code. And that causes some interesting opportunities in the Dask interface that we'll talk about in a minute. All right, so we talked about the tree growth thing a little bit before. I won't belabor that point. The only thing that I'll add here is if you're familiar with other frameworks like CatBoost or XGBoost, or even many random forest implementations, you may not be used to this notion of leaf-wise or what's sometimes called loss-guided tree growth. And all that means is for LightGBM, after this split is added, after this split is added, LightGBM isn't going to say, oh, well, the next split I have to add is at the same level to keep the tree balanced. LightGBM is totally comfortable growing these sort of lopsided trees, where maybe one side is a lot deeper than the other. All right, one really, really important thing to take away, one thing that makes the distributed learning idea sort of fast and feasible with LightGBM is this notion of discretization of continuous features. So this is an approach that's like very common now in gradient boosting with trees. You can use this approach in XGBoost, although it's not the default. You can use it in other libraries. And the idea is like this. When we're training these models, these nodes, these little circles, are added to one tree, one node at a time, right? So anything that you can do to reduce the time it takes to add a node and be confident that that node is actually improving the model, anything you can do to reduce that time is going to have a huge impact on the overall training time of the model. And so one trick that LightGBM uses, this sort of histogram approach, is to say, okay, imagine that we have this continuous valued feature, right? It has 7 values. We're working on big data here, folks. If I just take this data at its raw form, then there's 6 splits that I have to consider. I have to consider splitting the data at greater than 2, greater than 3, greater than 5, et cetera, et cetera, et cetera, right? And you can imagine that as your data set gets larger, and not even like that large, this can become a really, really large amount of splits really soon. But what you also may find is that the actual differences between values in a continuous feature might not really be that meaningful. They might just be like an artifact of measurement, right? So like, is an ambient temperature of 94.2 degrees, is that really meaningfully different to your humidity prediction model from an ambient temperature of like 93.1 degrees? I don't know, probably not, right? And so what LightGBM does is it does this pre-processing step where continuous features are bucketed into histograms. And that's described in the LightGBM papers that I mentioned before. I won't go into the sort of deep details of that. But the thing to take away is every feature in the data set is represented by these histograms, and basically the histogram boundaries, sort of the boundaries between slices of the distribution, those are the things that become candidate splits. So LightGBM in this example is only going to try one split, which is like greater than 1 for this sort of run length encoding of this feature. This is what makes distributed training fast and feasible, because now the actual like representation of the data that has to be shipped back and forth between workers is much smaller. And it's these histograms, these sort of like discretized summaries of the data that the worker processes are sharing with each other during distributed training. Okay, so the training process, in the training process, I've explained you add splits to trees. And the way that those splits are added is based on a loss function. A loss function, or you know, in LightGBM's parlance, an objective function, whatever you may call it. This is basically a function that describes how well a model's predicted output describes sort of the known true value of the target. And there are a bunch of these you may be familiar with. So in the regression space, you have like mean absolute error, mean squared error, you know, more esoteric types of loss like Poisson. For binary classification, like log loss is sort of the canonical standard. There are others, et cetera, et cetera, et cetera. I won't belabor this. But the sort of thing to take away here is that there is a sense of splits being guided by something. The tree growth algorithm is greedy. It's not just like randomly adding different rules and then combining them all together. At every step, the model training process has to say, okay, evaluate how much of an improvement in the loss function we could expect to receive from adding this split. And it's that evaluation that can be parallelized. Okay, so let's talk about how the tree growth sort of process ends, right? It has to end at some point. There are two types of stopping conditions in LightGBM. There are tree-specific stopping conditions and model-wide stopping conditions. So a tree-specific stopping condition, this says, okay, stop adding splits to this tree, and let's just like move on. The first of these is based on the total number of leaves in the tree. So remember that I said before that LightGBM grows trees leaf-wise, right? This means that the trees can be fairly like, for the same number of leaves, a LightGBM tree is expected to be, deeper than one from a more balanced tree growing approach. And so you can directly say here is the maximum number of leaves that I want to be added to each tree. And doing this can sort of like force your model to be simpler and more general as a way to control against overfitting. LightGBM does support a concept of max depth, similar to other tree-based algorithms. That says like, how deep will I go regardless of the number of trees? So you can see there's an interplay between those. There is another way that we control complexity through a parameter called min data in leaf or min sum Hessian in leaf. These are two very similar concepts that end up doing similar things. And what this says is basically like, okay, it's a little bit kind of like coarse to say, I'm going to limit the depth or the number of leaves. I also want to make sure that I never add a split that only matches like 2 samples from the training data, because that's very unlikely, to generalize well. And then finally, remember I said that the training process is guided by this objective function. The change in that objective function is called a gain. And you can say, hey, don't add a split that produces a gain lower than this threshold. For model-wide stopping, you basically have 2 options. You can say, train this many trees. And there is an option not yet supported in the Dask interface to do something called early stopping, which says, I'm going to give you a holdout data set. Stop training if some metric evaluated against that holdout training set, that holdout data set, doesn't improve for n consecutive rounds. Okay, let's talk about how to do this in a distributed setting. So there are a couple of methods for distributed training in LightGBM. The one that I think explains the concepts best and is most common is called data parallel training. And so that's the one that we'll talk about in this talk. In data parallel training, imagine that you have this sort of global data set like this. What happens is that data are horizontally partitioned across workers. And so horizontally partitioned means that each worker has a chunk of the data where they have a non-overlapping slice of rows, but all of the columns. In LightGBM distributed training, each worker has this list of either IPs or or DNS names, whatever, host names and ports for all of the other workers in the cluster. And so this is another thing that is maybe a little bit different than working in Dask, right? There's no concept of like workers just talk to a scheduler to get their information. Workers all know about each other. They know their own ranks, that's sort of like their unique IDs. They know how many other workers they're expected to be, and they basically all talk to each other. And they accomplish training through the collective operations that you may have learned about when you learned about frameworks like MPI. Although by default, LightGBM is not using MPI, but there's an MPI version. Anyway, so this is a really important thing to think about as we think about LightGBM distributed training. The workers are all talking to each other, and training proceeds in a sort of decentralized way. So there are steps where they can do work independently of each other, and then there are synchronizations, like when a new split is added to the current tree. Okay, once workers have started up, now they're all sort of connected to each other, and they can all send and receive messages over TCP. Now the training process begins. And so workers go through the following process over and over and over again. First, they look at their local slice of the data, and they compute something called gradient histograms. So those histograms, like I mentioned before, are sort of like slices of the distribution of the feature. The gradient part comes in basically summing up what the effect of the law, how to explain this? Basically summing up how poorly the model is currently explaining data that fall into that slice of that feature's distribution. Okay, so they compute all that stuff. Then workers take a collective action to share their local histograms with each other. Those histograms are a much smaller representation of the data than the full training data. So this is an expensive step relative to the rest of the process, but it's cheap relative to moving all the data around. Once they've done that, then workers perform all reduce to combine those histograms and to agree on the best split. And so they all say, okay, we've all looked at each other's stuff, like, here's what I think is the next split that should be added to the model. Once that best split is chosen, they sync up again to be sure that basically everyone has the same view of the local, of the sort of like the global state of the model. Then workers repartition their local data. They say, okay, now that we've added this split, these particular rows go to these two new leaf nodes. And then they keep repeating these steps until it's time to add a new tree. And then after they've added a new tree, after they finish this tree, then they repeat it again for another tree, et cetera, et cetera, et cetera. When the training process stops, then the workers shut down their listening sockets. They say, okay, we're done talking to each other. I am not accepting any more reservations, like we did this. And at the end of the training process, each worker holds an identical copy of the final model. So there doesn't have to be like another sort of sync up step at the end where you combine all of their local models. All of the workers have an identical copy of the global model. And when you do this in the LightGBM Python package, that model object is a lightgbm.booster Python object. Okay. Finally, let's talk about how this works in lightgbm.dask. So lightgbm.dask is the submodule of the LightGBM Python package that contains this sort of Dasky interface to that distributed training. That distributed training I just described, you do not need Dask to do that. You can achieve it with the LightGBM command line interface, or you can achieve it with the MML Spark project on Spark, and maybe other experimental projects that I don't know about. Okay, so first, if you feel inspired by this talk and you go Google Dask LightGBM and you're like, I'm ready to do LightGBM on Dask, this is sweet, you may find a library called Dask/Dask LightGBM. That library should be considered deprecated, and you should not start new work with that library. Do I have a slide about the history? Okay, so I don't. The brief history here is that there was a project created in the Dask org called Dask XGBoost that was added in 2017. About a year later, this project, Dask LightGBM, was added to the Dask org. But those projects were outside of XGBoost upstream and LightGBM upstream. And so as XGBoost and LightGBM changed, those projects, it was hard for them to keep up. And it was hard for them to influence XGBoost and LightGBM. And so in either 18 or 19, I don't remember, Dask XGBoost was actually upstreamed into XGBoost's main repo. And at the end of 2020, Dask LightGBM was upstreamed into LightGBM. So LightGBM completely absorbed Dask LightGBM, This PR into LightGBM that I've shown here, this is from the original creator and main maintainer of Dask LightGBM. So we've done that with Dask LightGBM's blessing. And now when you use LightGBM's Python package and you use the Dask interface there, you're getting all the things you got from Dask LightGBM plus a bunch more. All right. So if you've written LightGBM code before, or maybe XGBoost code, this interface should look really similar to you. The estimators from the LightGBM Dask submodule they follow the scikit-learn API. And the only difference is that they expect their data to be in Dask collections, either Dask arrays or Dask data frames, instead of Pandas data frames or something like that. Okay, once you start training, the first thing that LightGBM is going to do is split that data into something that we call parts internally. This is a structure that was borrowed from Dask LightGBM, which I believe borrowed it from Dask XGBoost. So this is like, code written years ago, just like carrying through all these different projects. And in this parts, the idea of this parts thing is that we're passing around dictionaries with the different pieces of training data. In this case, we have like data means the features and label means the target. And each of those dictionaries holds a delayed object for those pieces of the data. So we're passing around basically a list of dictionaries of delayed objects. And this is what we refer to as parts. Then LightGBM is going to compute all those parts. Notice we're not persisting, right? Because when training is done, we don't want to leave that memory like still used in the cluster. So we're just computing those parts, waiting for all of them to be computed. And then what LightGBM is going to do is it's going to look and see, okay, which workers hold which sort of chunks of the training data. And we're very careful about this. This is another pattern borrowed from Dask LightGBM. We're very careful about this to ensure that data isn't shuffled back and forth between workers as much as possible. And so what we want to be able to do is sort of have each Dask worker become a LightGBM worker that trains only on its local sort of slice of the data. All right, after that, we're going to set up a LightGBM network. This uses some of those same parameters that I talked about before, but lightgbm.dask is actually inspecting the state of the Dask cluster to come up with good values for these parameters in a way that LightGBM's core library will understand. And so, for example, for the list of machines, in LightGBM parlance, each worker is a machine, but for Dask's purposes, this will totally work if you have like 2 worker processes on the same physical host. We're going to look for only the addresses of Dask workers that hold some of the training data. So we're not just going to say like take all the workers in the cluster. All right, after that, we're ready to start training. And so what's going to happen is this function train part, we're going to create 1 task per worker running this function. And this function is doing a ton of work. And I'll show you in a second. But one thing that's like important to note here, I think, is LightGBM has to use client.submit and be very, very specific in doing that. So if you notice, we have like workers equal worker, pure equals false. We're going to talk about in a second why it's important for LightGBM to know I'm scheduling this exact task onto this exact worker. And then at the end of training, you can see here, what we're going to get back is a LightGBM booster object. And that's just sort of the train model that'll be returned into the object on the client. All right, so let's talk about train part really briefly. What's happening here is when this function is called, it's going to be called once on each worker. This function will concatenate up all of its local parts. So all of the individual chunks of the data, you could have like 100 partitions and 3 workers, right? So even when you get to just the data that's on 1 worker, they're still split into different pieces. Those are going to be combined up together. Then LightGBM just proceeds with training. This model factory is going to be one of the LightGBM scikit-learn estimators. Working with training like this means that all of these worker processes, they talk to each other, they perform these collective operations like I talked about before. And then at the end of training, they return themselves. Like just return a fitted model object and we're good to go. All right, so let's like really talk about the meat of this. These train part tasks are long running tasks. So you can see sort of like, look at how long this one train part task is from a run I did last night compared to the data loading. And this is like, it can be way longer than this. So what happens is these tasks, once they start up, then they're doing all the LightGBM distributed training stuff. Workers are like looking at their local data, computing feature histograms, sharing that data around, communicating with each other about the best split. And at that point, all of that work is being done without Dask's knowledge. This is just like, as far as Dask is concerned, this is a long running Python process that's just like waiting for some other C++ code to complete. And that brings some interesting challenges with it. So for example, LightGBM training can't benefit from work stealing. So LightGBM training, in the way that it's set up, it violates this kind of idea from working with Dask that tasks can be moved around to different workers if the worker that they're on is overloaded or having some problems. You can't do that with LightGBM distributed training, because the training process, the way the communication works, it relies on a fixed list of worker IPs and ports. Similarly, if a worker is restarted or just dies completely during training, training will fail, like game over. Like you saw before, when we run these training tasks, LightGBM has to be extremely specific in its client.submit calls about where those tasks run. And then because Dask can't really see what's going on in these processes, because it's not, it's just sort of this long-lived thing that is doing so much work that there are like periods of low memory and CPU utilization, periods of high memory and CPU utilization. You're not going to have a good time using adaptive deployments. Adaptive deployments, you might expect to make bad decisions in the face of this work, just because LightGBM is doing so many different and sort of diverse types of work within that task. Reliably scheduling other work onto the cluster while you're training could get a little dicey, again, for the same thing. And you pretty much need to disable task level timeouts, because the work is being done in one task, right? Using task level timeouts, like, you're going to have to predict how long the entire training process will take, which can be difficult to do.
Hey, James, just a quick update. We've got about 1 minute left.
Okay, perfect. We're on the last slide.
Cool.
That is the extent of what I wanted to talk about today. And the last thing I want to do is pitch to you. If you're interested in LightGBM and you know stuff about Dask, please come contribute. We've had great contributions from the Dask community so far, but there's still a lot of work to be done on this project. You can try out LightGBM yourself first if you'd like by going to these links, and I'll share the links to all these slides. And you can come into LightGBM, github.com/MicrosoftLightGBM, find the issues that are open, and we really, really would love some help from the Dask community. And with that, I will yield my time. Thank you so much for coming, and enjoy the rest of the conference.
Awesome, cool. Well, we started a couple minutes late, so we can do maybe like one question now. If anybody else has some more questions for James, definitely go on the Dask Slack. You can reach out to him there. You can start a conversation on the Summit's talk channel. I did have one quick question that we can do. So I obviously, like, Dask is really great for when you can distribute the training with large data sets, or you want to do things faster. What's kind of your recommended way to then go from that to kind of deploying a model? And then, do you need Dask? Is there ever a scenario where it would be helpful to use Dask on the deployment side?
Yeah, great question. So in both XGBoost Dask interface and LightGBM's Dask interface, the model object that you get at the end is just the regular old booster, just like the core sort of model format that all of the different LightGBM or XGBoost interfaces produce. And what that means is you could have Dask as a training time dependency. You could say, I have so much training data, like I need to use Dask, but not need Dask as a scoring time dependency. So you can take that booster and you can just, like, you could use it in like a C++ Lambda on AWS or something. You can actually dump one of those model objects that's like a Dask estimator to its scikit-learn equivalent that just has dependencies on like pandas and scikit-learn. There are tons and tons of ways to do it, but yeah, I'm really glad you asked that question. The key thing to take away is with LightGBM's Dask interface, you can use Dask to speed up training or make training of a larger model or on larger data possible, but that does not mean you're signing up for using Dask to deploy the model.
Sounds great. That's awesome. Well, thanks again, James, for the talk. I really appreciate it.
All right, thank you so much.